Here's two magnets. The north pole of one magnet is on the right side, and the south pole of the other magnet is on the left side. Those two magnets both produce a magnetic field. And the magnetic field of those two are going to interact with each other such that it's going to look something like this, at least directly in between those two magnets. We're going to call that an external magnetic field. It's a magnetic field that's already there. Now, I'm going to draw another thing that produces a magnetic field. This time it's going to be a charged particle, a negatively charged particle that's going into the page. That magnetic field is going to look something like this, circular in nature and counterclockwise in direction. What if those two magnetic fields encounter each other or interact with each other? In other words, what if that wire that I have going into the page is actually going into the page right there, right smack in the middle of the magnetic field that was generated by the two magnets? Let's draw it up there and see what it looks like. We have two magnetic fields completely different from one another, but interacting with each other. When two magnetic fields interact with each other, there's going to be a force that acts between them. In other words, this wire that produces the circular magnetic field will experience a magnetic force. These two magnets that produce the straight magnetic field will also experience a magnetic force. Now, it's a little bit tricky to describe this magnetic force. It's not just as simple as saying, oh, okay, the wire is attracted to the North Pole or the wire is attracted to the South Pole, because it isn't. We have to use another hand rule, a third hand rule, in order to determine how this force acts on the wire and on the external magnets there. We're going to call this the third rule, which is the hand rule for deflection, or the deflection rule. In the wire grasp rule and in the coil rule, there was only two variables, your thumb and your bent fingers. Remember, in the wire grasp rule, it was thumb current, fingers field. In the coil rule, it was fingers current, thumb field. In the deflection rule, we're going back to saying your thumb points in the direction of the moving charge or in the direction of the current. But your fingers are not going to be bent this time. Your fingers are going to be stretched out, just like this. Now, be careful. Okay, don't just stretch them out with your thumb pointing in any which direction. Your thumb and your fingers continue to have to be 90 degrees to each other, like this, but your fingers are going to be flat this time. So your stretched out fingers are going to point in the direction of the external magnetic field. And what do I mean by the external magnetic field? The magnetic field that was already there, not the magnetic field that's caused by the moving charge. It produces a magnetic field. You can see that, it's circular. But that's not the one we're talking about here with the second variable. My stretched out fingers point in the direction of the external magnetic field. In this example, it was this magnetic field, the one that points to the right, the one that's caused by the magnets. Maybe the external magnetic field could be produced by a bar magnet. Maybe it's produced by an electromagnet. Maybe it's produced by the Earth. It's something that's already there, not the field that's caused by the moving charge. The third variable, and there are three variables in the deflection rule, the third variable tells us which direction the force is in. Thumb in the direction of the particle into the page, fingers in the direction of the external magnetic field. The palm of your hand, the flat palm of your hand, points in the direction of the magnetic force. So you can see in this example, my flattened out palm will point upwards toward the top of the page. That's weird, right? You got a particle that's moving this way into the page. You got a magnetic field that's going this way towards the right side of the page, but the force is upwards toward the top of the page. It's weird, but it is what it is. If the charged particle is moving perpendicular to the magnetic field, the magnetic force will always be perpendicular to both the motion of the particle and the field. So if you've got one on the x-axis, one on the y-axis, the third variable has to be on the z-axis. If one's on the x and one's on the z, the third variable has to be on the y-axis. They must be perpendicular. All three of those variables must be perpendicular to each other. If, by the way, the charged particle is not moving perpendicular to the field, this rule doesn't work. We can't do it. So any question we're going to see is going to involve the charged particle being perpendicular to the field. Here's another little description of it. You can write down all or none of this if you want, okay, whatever works for you. If you wrote down what was on the last page, probably covers it, but if you like to have it in words, that's fine too. We can find the direction of the force using that hand rule for deflection, but what about the magnitude of the force? How big the force is, its value? Well, we're going to see the first equation in this entire unit. Here it is 4 days in. We haven't done any math yet. Now we're going to start. The equation that describes the magnitude of the force is given below. Fm, the magnetic force, is equal to QVB. The magnetic force measured in newtons is equal to the charge measured in coulombs times the speed measured in meters per second times the magnetic field strength measured in Tesla, which is usually abbreviated with the symbol T. Now, there's a couple little notations here that you might not be familiar with here. First of all, two of these variables have vertical lines around them. Do you remember what that means? We've seen that before, but not very much. Those vertical lines mean absolute value, right? In other words, force is a vector, magnetic field is a vector, but this equation does not require the direction of the magnetic field in order to use, nor does this equation provide for us the direction of the force. There is a direction of the magnetic force, but we're not going to find out what it is from the equation. That's okay, because we can go back to the hand rule for deflection to find out what the direction of the force is. We don't need the equation for direction. We need the hand rule for direction. We need the equation for the magnitude of the force. What about this little thing right here, this little notation that I don't think we've seen that at all before. It's an upside down T. What do you think that means? It's a reminder that this equation is only valid if the speed of the particle and the magnetic field strength or magnetic field direction are perpendicular to each other. They must be perpendicular. This equation isn't valid if they're not perpendicular, any more than the hand rule for deflection is valid if they're not perpendicular. In other words, we can only do problems, both magnitude and direction, where the charged particle is moving perpendicular to the field. That's not quite true, actually. If they're perpendicular, we can do this in addition to the hand rule for deflection. If they're parallel, in other words, the charged particle is moving that way, the magnetic field is that way, or the charged particle is that way, the magnetic field is that way, parallel to each other, it's even easier. This isn't hard, but if they're parallel, the magnetic force is 0. Here's the field, here's the particle. F is equal to QVB, hand rule for deflection. Here's the field, here's the particle, force is 0. There is no rule to determine the direction of a force that's 0, just no force. What if it's like this? You have to modify that equation a little bit, but we don't do that in Physics 30. It's not all that hard, actually. If it's not perpendicular or parallel, it's not crazy hard. But you won't see that until probably your first year of university if you take a physics course. Okay? Don't sweat it. Okay, it's not going to be much harder than what we've just done. It's just not required for us. So the only things you're going to see in Physics 30 are, they're almost always going to be perpendicular. But if they're not perpendicular, they'll be parallel. And if they're parallel, it's even easier because the force is 0. Got one example for you, and then we're going to wrap it up for the day here. Example 12.1 says an electron is traveling at a speed of 3.2 times 10 to the 5 meters per second, perpendicular to an external magnetic field. All right. For us, it's always going to either be parallel or perpendicular, probably perpendicular 99% of the time. If it's parallel, the force is 0. If it's perpendicular, we're allowed to use the equation and the rule that we just learned. It's perpendicular. I wish it was parallel. The force would be 0. We'd be done. It's not. It's perpendicular. So we got to do a little bit of math and a hand rule here. The magnitude of the force is simply going to be QVB. It's an electron, so the charge is 1.6 times 10 to the minus 19. Speed is 3.2 times 10 to the positive 5. And the magnetic field is 2.2 times 10 to the minus 1 Tesla. Multiply those together. We end up getting 1.13 times 10 to the minus 14 newtons. That's the magnitude of the force. That's the best that we can hope for with that equation, is the magnitude of the force. Remember, if they're parallel, don't use the equation. Just say the force is 0. If they're perpendicular, use the equation. If they're not parallel or perpendicular, don't do it. It's not a question we have to be able to do. Okay, what about the direction here? Hand rule for deflection, right? Thumb in the direction of the particle, which is, they try to draw it 3 dimensions here, but they mean it to be into the page. Fingers field, which goes from north to south. Palm's going to point which way, Haley? Up toward the top of the page. There we go. I want you to do only question number 1 on page 599 for homework, and that should go ridiculously quick for you. You can probably finish your homework tonight in literally 1 minute or less.